So we have a great program this morning featuring Dr. Rao, who will be speaking on rare earth elements, which I'm sure you won't find them in your backyard, but your household should have some of those elements. But before we get started with the program, would you please rise for the Pledge of Allegiance? I, Christian Escalante,
to the flag of the United States of America, and to the republic for which stands one nation under God, indivisible, with liberty and justice for all.
As you know, our programs are recorded live on Zoom. So for that, we'd like to thank the Coronado Public Library and its staff, especially Selena Valladolid in the back, who's in control. And for those of you at home, please mute your computer or device, and please turn off your camera. You may use the chat box function for the Q&A portion of the program that will follow the presentation. The recording will also be available to view on the library's YouTube channel a few days after this program. For those of you in the room, please mute your mobile phone and please hold your questions until the end of the program. Our coffee this morning is provided by Alex of Amalo Brew, the coffee cart here on the front of the library. And we do ask for a $3 donation for the coffee. You may also donate just to help us provide these services here at the library. Our speaker next month, you will not want to miss, will be our own board member, Vice Admiral Charles Martolio. That will be on April 24th here in the Wynn Room. But now our own board member, retired Rear Admiral Stephen Clary, will introduce the program. Steve.
Thank you, Christian. Hear me?
Yeah.
Thank you very much. Good to see so many of you here today. My name is Steve Clary. I've been a longtime board member here and pleased to welcome one of my colleagues to talk about rare earth elements. And how many of you watched the 60-minute show on Sunday on that? An excellent program. And Maud is going to talk about that as well today. The subject is rare earth elements. What makes them important? Are they rare? And the fact that the United States is dependent on China almost exclusively for this important materials, which we find in every bit of consumer electronics, your automobiles, defense products, and many, many other applications. He will talk about what they are, why they're important, and how the U.S. is responding to this critical national priority for materials. Maud is a chemical engineer, semi-retired. He has a PhD in material science from Pennsylvania State University. I'm pleased to bring him here today. He is part of our stable at the Osher Lifelong Learning Institute up at UC San Diego, where he and I are colleagues. For those of you who aren't familiar with the Osher Institute, it is a 50-year-old organization having lectures twice a day for adults over the age of 50. We bring academics, we bring people from industry. We even have the Vice Admiral Charles Martolio annual memorial lecture.
It's not a memorial.
Not a memorial.
So without further, by the way, we are having an open house at the Osher Institute tomorrow at 9:30. And I see nodding of head. Bob, good to see you here today. You all are welcome to attend and hear about this wonderful program. But more important is to bring my good friend and colleague, Maud Rao, to the podium to talk about rare earths. Thank you.
Thank you very much, Steve, and thank you for the kind invitation to come and talk to you about rare earth minerals. As Steve said, I'm a chemical engineer. I have worked in the semiconductor industry for 36 years. I retired in 2022, but materials have always been my passion. What makes them work, why they're important, and how to get them to be useful for us as a culture and as a society. And I want to talk today about rare earth elements. As Steve mentioned in the introduction, they're not really rare, and we'll talk a little bit more about that. But I want to give you some perspective as to why they are so important for our modern world and the role that they play. We'll talk about a little bit of the history of rare earths. We'll talk about what makes them unique and give you an example of how they provide exceptional performance, even when they are used in very low concentrations in things that we take for granted, like magnets. They are vitally important to our military infrastructure, and we'll talk a little bit about that, and then talk about what's going on in the world today and how the United States is responding. So here's the agenda. What are rare earths and why are they important? We'll talk a little bit about the process of extracting rare earths. It turns out that rare earths are unlike other metals in that you don't get a vein of rare earth materials. They're usually mixed with other materials, and so it makes processing rare earths and purifying them quite challenging. We'll talk about the geopolitics of rare earths. Steve mentioned that China is the dominant player in rare earth materials. In fact, China produces 90% of the rare earth elements. And when you take a look at where these materials show up in our modern society, you can understand the vulnerability that we have with having rare earths come from China. And we'll talk about what the United States is doing to respond to that challenge. And where I'm not sure I can talk to you about where we're heading, but I think we are making progress in reducing our dependence on Chinese sources and diversifying the supply chain for rare earths, which is going to be very, very important, both commercially and to our military. So let's talk about the fundamental question: what are rare earths? So here's the periodic table. The rare earth elements are those elements that are highlighted in red. Okay? They are relatively high molecular weight materials, and what makes them unique is that they have a very interesting and different structure in the electrons that orbit the atom that gives them unique properties. And we'll go a little bit more detail on that a little bit later. But historically, rare earths date back to the late 1700s. In 1788, there was a black rock that was discovered in Sweden. Nobody had ever seen such a thing before. And because it was rare for its time, one of the names it was given was rare. And the definition of earth at that time was a material that could be dissolved in acid. Hence the name rare earth. Throughout the 1800s, rare earths were, a wide variety of rare earths were discovered and added to the periodic table. You know, the 1800s, from a chemistry point of view, was a very interesting period because people were trying, scientists, chemists were trying to be the first to discover a new element to add it to the periodic table. And so there was a great flurry of discovery in the 1800s, and most of the rare earth elements that are on the periodic table were discovered then. And as I mentioned, it's the organization of the electrons around the atom in rare earth elements that really make them unique and give them unique properties. And we'll go in a little bit about more detail of that in a few slides. But as I said, rare earths are not unique. Rare earths can be found all over the world. And the challenge is not finding the rare earths. The challenge is twofold. First, to find rare earths that are of sufficient concentration that make them economically viable to recover. And the second challenge is recovering them without as effectively and as efficiently as possible with minimal environmental impact. Rare earths show up in a wide variety of materials that are part of our normal life. We see them in magnets. So I was talking to Steve about his Tesla. I also drive a Tesla. If you drive a Tesla, you have motors that contain rare earth materials. the unique property, one of the unique properties of rare earth magnets is that they have a very high magnetic force for their given mass. So you can make motors that are much smaller to drive whatever you're trying to drive. So for example, in your cell phone, there is a speaker, and that speaker contains rare earth elements because they can make very small magnets that can fit inside your cell phone. If you use AirPods, they have rare earth elements in the magnets that are used in the AirPods. So these very high-powered magnets become very, very important in developing materials and products that can be much smaller, much lighter, and much more efficient and effective. Dilute quantities of rare earth materials are used as phosphors to emit light in displays and fluorescent lighting, in medical imaging, in fiber optic cables. So in fiber optic cables, they dope a small quantity of a material called europium. And it turns out that even with very low concentrations of europium, the glass fiber becomes much more transparent to the laser light that's being passed through it, so that you don't have to have amplifiers as closely apart. Okay? So a very small quantity of rare earth materials can have major impact on the performance of important products for our lives. Rare earths are used in metal alloys. Again, small quantities of rare earth materials are used in aluminum to significantly strengthen the aluminum, which makes commercial aircraft and fighter planes a lot lighter. They're used in polishing. Several of the oxides of rare earths are very hard materials, and you can use them to polish glass. They're used as UV protective coatings. And about 90% of glass lenses that are used in cameras, particularly on your smartphone, have small quantities of rare earths on them to make them more opaque. Yes?
Sorry, I don't mean to interrupt. Could you say the names of some of these elements?
I can. Let's go back to the. Oh, okay. Sorry, you can't see them. I see. I'm sorry. So neodymium, terbium, dyspropium, praseodymium. Okay, they're all the elements along the lower part of the periodic table. Yeah, and these are the chemical symbols. If you'd like, at the Q&A, we can go back and take a look at where they are on the periodic table. So most of the ones that I'm showing are that highlighted region on the bar at the bottom. Yeah. Yeah, some of them are pretty tough even for me as a chemist. Oops, sorry, wrong way. They're used in electronic materials, in ceramics, and sensors, and capacitors. They are used as catalysts. So your catalytic converter in your car may have some rare earth materials in it that help it convert the hydrocarbons and carbon monoxide to carbon dioxide and water. So they're used almost in everything that we touch. You wake up in the morning, and probably when you turn on your coffee pot in the morning, that little digital display might have some rare earth materials in it. Okay, and the LED light that you turn off at night may also have rare earth materials in it. So we can't get away from them. But let's talk about the magnetic properties and what makes these magnets so interesting. So if you consider an iron bar, right? Typically we have magnets made of iron. If you, on a microscopic level, look at what's happening in the iron bar, there are domains of tiny little magnets, okay? And each one of these arrows on the right-hand side indicates the direction of that magnet, north and south. And you'll see that in an average iron bar, those tiny magnets are randomly oriented, okay? So that the bar itself has no net magnetic properties. But if you then subject that to an external magnetic field, you can get those tiny domains of magnets to line up. Okay? And if you have the right material, in the case of iron, and you remove that external magnetic field, those tiny magnetic domains will remain aligned. Okay? And that's why you have a magnetic material. And when we think about magnets, we think about three different properties that define the figure of merit for how good of a magnet it is. The first is called the coercivity, which is the ability of the magnet to resist going back to that random orientation of those micromagnetic domains, right? The higher the coercivity, the better and the longer that magnet is going to survive as a magnetic material. The second is the magnetic density, which is how magnetic is it per unit mass, right? You can imagine that the higher the magnetic density, the less material you need to accomplish the same task. And that's why we use rare earth magnets in earbuds, because you don't want to have a heavy earbud hanging off your ear. You want something light and portable. And so that's why we do that. And then the third is the working temperature. And in many applications, the working temperature becomes very, very important. For example, in a fighter plane, that's where you have a magnet that's near the engine itself, it may see very high temperatures. And you want something that's going to be able to withstand those temperatures and not get demagnetized. So let's compare just a couple of the magnetic properties of rare earth-based magnets as opposed to more conventional magnets. So on the chart on the right, we have on the left a bar that says FeO. This is an iron oxide magnet. The next says aluminum, nickel, cobalt. So this is a very common magnetic material. Then you have samarium cobalt in the salmon color, and neodymium iron boron in the green. Okay? And what we're plotting is the working temperature of the magnet as a function of the magnetic density. So remember that the magnetic density is how magnetic it is per unit weight. Okay? The higher magnetic density means that you can use less of that material to accomplish whatever task you need to accomplish. And you can see that the rare earth-based magnets have a much higher magnetic density, which is very good because you need less of them to do whatever you want to do. But they also have a very impressive working temperature. So that's why rare earth magnets are used in high temperature applications, because not only can you use less of them, but they can operate at high temperatures without losing their magnetic properties. And with that, rare earths have been found, or can be found in just about every aspect of our lives. So this is a drawing of where you can find rare earth materials in an electric vehicle, either a hybrid electric vehicle or a 100% electric vehicle. And you can see they're in the catalytic converter, in the screens, in the magnets used in the power steering systems, hybrid batteries. They're used to polish the glass. Just about every aspect of this automobile could have either rare earths in it or rare earths used in its manufacture. And with the advent of more renewable energy sources, rare earth magnets find themselves in generators that are used in wind turbines, in electrical components used for solar energy systems, and advanced battery systems. So they are ubiquitous in our lives today. But in addition, they are critical components for our military. And if you look at where rare earth elements are found in military hardware, they're found in fiber optics, in lasers, in guidance and control systems, in guided munitions and radar and sonar, electronic warfare. All these functions within the military, in one way or another, touch or are touched by rare earth elements. And I mentioned the importance of them earlier on, but if you look at the total quantities of rare earth materials used in, say, an F-35 fighter plane, okay, it's almost 900 pounds of materials, maybe 950 pounds of material. Okay, 2,600 kilograms or over 5,000 pounds of material in a destroyer, 9,000 pounds of material in a submarine. Okay? This is why having China control 90% of the production of rare earth materials becomes very, very problematic, not only from the commercial point of view, but for our military. And this is why it has really been brought to the forefront in the past, I'd say 2 or 3 years, the importance of trying to find independent ways of managing the supply chain for rare earth materials. You know, the United States had a very dominant position in the production of rare earth materials with the rare earth mine that's up in Mountain Pass, California. That was one of the leading producers of rare earth materials into the 80s and 90s. But because of environmental regulations, because of market conditions, that mine closed. It was reopened a few years later. It closed again because by that time China had taken a dominant position in rare earth materials and was able to undercut the price that was being charged by the mine here in California. But more recently, if you've seen the 60 Minutes program last Sunday, a group of investors have taken over the ownership of that mine and are really working with the US government to provide that mine as a source of independent rare earths separate from China. Okay. So let's take a look at how rare earths are processed, because it's not only the mining of rare earths that it's important, but the processing of rare earths. As I mentioned, rare earths are not rare in the definition of rare. So if you compare rare earth materials to gold, for example, okay, most rare earth materials are more abundant than gold. But the advantage of mining for gold is you can find a vein of gold, or you can find nuggets of gold. You don't find veins of rare earths or nuggets of rare earths that are not that are of high concentration. Okay, typically rare earth materials are less than 1%. If you've got a rare earth material, a mine that has rare earths that have 2 or 3%, you're really in good positions. And some rare earth mines around the world have about 5% rare earths. So which means you need to separate 95% of the stuff you don't want from the stuff you actually want. And that is a real challenge. The other challenge with rare earths is quite often they are mixed with radioactive elements. Okay, often they're found in the form of sand and mixed that contains rare earths and other things. And you've got to separate the rare earths from these radioactive materials, and that becomes a real challenge. Well, how is that done? Okay. There are actually two ways of harvesting rare earths. We'll cover that a little bit later, but let's take a look at the mine in California, for example, or mines in China that have a lot of rare earths, and talk about how they're actually processed. So there's a series of steps that are involved in going from the rare earth ore to the concentrated rare earth. Well, first you're going to quarry the material wherever it is. It involves evacuation. You have to then, excavation. You then have to pulverize the rock. You need to separate it. You need to concentrate the rare earth components of that rock. And usually it's a mix of rare earth compounds. So then you have to separate each individual rare earth and convert it to the material of interest. So after, I'm sorry, I'm going the wrong way. Rare earths, other than being in a sand form, can be found in a leachable form. Okay. And this turns out to be a little bit easier to do, but not less environmentally damaging. So if you've got a field of water-soluble rare earths, what you do is you pump water into the ground, and you have a way of getting that water out, and the water then dissolves the rare earths, and then you take that rare earth-containing liquid that you extract, and then you do downstream processing. So let's take a look at some of the details. So you take the ore, you pulverize the ore, and then you need to separate out from that powder the materials that contain rare earths versus the materials that don't. And so you add some organic compounds which attach to the particles of interest. Those particles then float. The rest of the stuff settles out. You discard the material that settles out. You take those materials that float on top. You treat them with acid to try to dissolve as much of those rare earth elements in those rock powders as possible. You then have to discard the acid waste from that, as well as some of that powder that does not contain rare earths. You separate out the solid materials. You then leach. Go down the bottom, you leach the remaining powder to try to get out as much of that rare earth material as you can and recycle it back. You then extract the individual rare earth compounds that you want, then convert those compounds into the metal, and then send that to refining to make the magnets or whatever you're trying to do. So it's a multi-step process using a lot of different chemistry with the potential of having radioactive waste in the back end. Now, if you just do the leaching method, as I mentioned before, water-soluble rare earths, you're doing the back end of this, which is basically taking the water that contains the rare earth elements, separating out the individual elements, and then passing them on to refining. But if you look at it, to make 1 ton of rare earth metals, you need to process about 2,000 tons of ore. So it's a very, very time-consuming, costly process to make rare earths. And if you look at the waste products, you can get up to 20,000 gallons of wastewater that you need to process, about a ton of radioactive material if the source has thorium and uranium in it, about 30 pounds of dust, and about 400,000 pounds of toxic gas. And you have to deal with all of this in the processing of rare earths. And the Harvard study indicated that to make a ton of rare earth materials, you're going to have about 2,000 tons of waste products. Many of them you have to deal with to prevent environmental contamination. And rare earths do affect the human body. The routes of inhalation are through, the routes of exposure are through inhalation, through ingesting the particles, and through the skin. And it can have effects like memory loss, damage to the cell, chronic respiratory problems, infertility, etc. So if you're in or near a rare earth mine, you need to be very cognizant of the potential environmental impact of the processing of rare earths. And this is one of the things that actually led to the abandonment of the Mountain Pass mine years ago. But technology has changed. Let's talk a little bit about the geopolitics, because I think that's been in the news a lot in the last year, maybe a little bit longer than that, about what is our vulnerability to rare earths and how are we going to manage it. Well, the demand for rare earth materials is continuing to rise globally. It's expected that by 2033, the demand is going to increase by 40%. That's primarily because of the move towards renewable energy sources. But the United States is actually going to exceed that, and it's expected that we're going to need almost 3 times as much rare earths by the middle of the next decade as we do today. That's a challenge in and of itself, but the challenge is multiplied by the fact that when you look at where the rare earth reserves are, China controls about almost 40% of the known global reserves of rare earths. The BRICS countries contain about 72% of the global reserves, and the United States has only about 2% of the proven rare earth reserves in the world. So the first problem is, do we have even access to rare earth materials? The second problem is, do we have the capability of processing those materials domestically, or do we need to rely on an external source? Well, China has been investing in rare earth processing since the late 1950s. Okay? And today, they process 90% of all the rare earth materials used globally. So it's a significant supply chain risk to be reliant on China to supply rare earths. Now, in the 60s and 70s, it may have been less of a concern since we had our own domestic processing, but today it's really, really a strategic vulnerability. As I mentioned, in the late 1990s, the US stopped the processing of rare earth materials. We were still mining materials, but we were shipping them to China to do the processing for us and then buying back the magnets and other things from China. You'll see why we did that. I'm not saying it was the right thing to do, but you'll see why when you look at what and how China is processing rare earth materials, and we'll get to that in just a moment. But you know, this issue of rare earths, and rare earths is one of a list of about 100 or 120 different materials that are called critical materials. Okay? And the US Geological Survey every year puts out a critical materials report. that talks about what are these 120 or so critical materials, how they're used in the United States, what are the sources for this country, and they calculate something called the net import reliance. Basically, the net import reliance is the percent of domestic consumption that we rely on an external source, from a source outside of the country. And so we're plotting here the net import reliance on the y-axis as a function of time. From 2010 to about 2015, we're actually reducing our dependence. The net import reliance was going down, so we're reducing our dependence on rare earth materials. But then we started electric vehicles, alternate energy sources, and the reduction in the total amount of production in our domestic rare earth supply. And so we needed to rely more on external sources. And for a long time, the net import reliance was 100%, meaning 100% of our domestic requirement was being filled by imported sources. Okay. Now, lately, that number has gone down, which is a good thing. But when you're relying that highly on imported sources, and that source is a strategic challenger, that is a strategic vulnerability which we need to manage. And we are now starting to work very hard to try to manage that and balance the supply chain risk with the need for domestic growth. But let's take a look at the largest rare earth mine on Earth. It's located northwest of Beijing in Mongolia. It contains the bulk of China's known rare earth reserves, and it's operated by a state-owned company called Baotao Iron and Steel Group. Okay. So the Chinese government is actually managing this mine and the processing of the rare earths that come from it. It is a huge facility. Here is a satellite photo of the facility in China. It's about 11 miles east to west and 5 miles north to south. You can see that it's an open pit mine. Okay? There are several segments to this open pit mine. There are ponds that trap the residue that comes from rare earth processing. There are dump sites for the solids that come off the mining process. So this facility takes the rare earths, does the pulverization and separation, and then sends the material to another facility to actually make the rare earth metals. Okay, and that rail line that I'm showing you down below is the line that takes the rare earths to Baotao, where the materials are actually processed. The challenge for China is years ago when they started this, they were not very concerned about the environmental impacts. So there's a lot of radioactive dust from this facility. The mine wastes are laden with chemicals and heavy metals and radioactive compounds. They are dumped into tailing ponds, and there is toxic air pollution that is emitted from the mining and processing steps here in this section of China. And there is, I don't know whether you saw, let me back it up. There is a town right here. There's a town right here, Bayon Obo. And in that town, there's a elementary school, which is surrounded on all sides by the rare earth mine. So it's a real challenge for the people that work there. I mean, they have a economic incentive to stay there because they are working at that location, but it's not one that's well managed environmentally. I mentioned before the leaching of rare earths that are soluble in water, right? And many of those type of leaching facilities are located on the border of China with Myanmar, okay, in the region that's highlighted in orange. Okay? And basically what they do is they go to a mountainside. At the top of the mountain, they drill boreholes. They pump water in the top, and on the side of the mountain, they cut pipes that recover the water that's now laden with rare earth materials, direct them to these ponds where they are eventually pumped out and sent for processing. And the Chinese companies that are in the rare earth business have invested a lot of energy and money in the border towns along Myanmar. for example, if I can get this to work, there we go. In 2020, there were 130 mines, and just 4 years later, it almost doubled the number of mines. And what happens here is they will extract as much as possible from a hillside, and then just leave whatever they've got, move to the next hillside, drill another set of holes, and just march themselves down the mountainside to try to extract as much of these materials as possible, leaving behind all the equipment and the runoff, which then impacts groundwater and impacts the residents in the surrounding area. So it's a messy business, at least in China and in Myanmar. Well, let's skip ahead to last year. China, of course, is a growing economy. It's the fastest growing economy in the world. One of the things that they do lag behind compared to the West is in semiconductor technology. And right across the waterway is Taiwan, which is the leader in semiconductor processing in the world. 90% of the most advanced semiconductor processing chips are made in Taiwan. And China would like to catch up with Taiwan. And so they had been developing their own semiconductor industry. The United States, to kind of slow the progress of the Chinese semiconductor industry, had put restrictions on the export of technology and materials to China. And as a response, China responded by severely restricting rare earth exports and putting licensing requirements to companies, as well as limiting the applications that the rare earth magnets can be used. And so now this has heightened our sensitivity to the importance of rare earths more than anything else probably in the past. And we've been doing a lot of things as a country to try to fill in the potential gaps that will arise from any embargo of rare earth materials by China to the United States. And you hear a lot about Greenland, right? There was a discussion about Greenland. It's kind of died down now, but last fall about the importance of Greenland. And, you know, that actually is strategically very important to the West. Patuxent Space Base is located in Greenland. It's the northernmost installation for missile warning and defense systems. And so it's a very important part of North American defense. Logistically, it's in a very important position because as global warming continues, it's anticipated that northern routes to the east are going to be more applicable. And Greenland is located at one of the choke points across North America. And so kind of like the Straits of Hormuz is today, those who control that choke point of commercial traffic will have an advantage. So this is the impact of Greenland from a strategic perspective, but it also has an impact on rare earth materials because Greenland has some of the most important critical rare earths that have been untapped. And some of those rare earth deposits in the southern part of Greenland have pretty high concentrations of rare earths, more than 2% of rare earth material. So if you could extract that material, you would have a good source of rare earth materials that you could then use to process. The challenge is convincing the people of Greenland that it should be mined because there are a lot of environmental concerns on Greenland. The sources of rare earth on Greenland do contain radioactive materials, and there was a 2021 law in Greenland that bans the mining of materials that have above a critical level of uranium, which these deposits do. And there's a question of national sovereignty, right? There was a discussion at one point about the United States trying to buy Greenland or taking over Greenland. I think that's died down a little bit, but the population of Greenland is not very much in favor of becoming part of the United States. And a poll just in January suggested that the United States was, or the citizens were opposed to taking over Greenland, at least by force. So what that means is now we have to negotiate with the Danish government to get access to Greenland's rare earth materials. But the problem with Greenland is it doesn't have the infrastructure, and it's going to require a huge amount of investment of infrastructure. So if you just compare the entirety of Greenland to what we have in Texas, and look at the number of road miles, the number of ports, the amount of railway lines, you may be able to get to the rare earth materials, but getting them off of Greenland to the processing is going to be a real challenge. So if Greenland becomes an important source of rare earth materials, it's likely to be in the long term until you can negotiate with the Danish government, convince the Greenlanders that it's a good deal for them, and to invest the billions of dollars it's going to take to invest in infrastructure in Greenland. It's important, but it's not going to be a solution to our immediate rare earth problem. So how do we address this? Well, we have to have strategic alliances, and we are doing that. So recently, the United States and Australia signed an agreement to try to counter the role of China in the rare earth marketplace. Okay, it's a bilateral agreement. Australia has some very large rare earth reserves and technology for processing rare earth materials. So it makes sense for us to partner with Australia to try to do two things. One, get access to the mineral deposits, but also get access to the Australian technology. And so we have a cooperative agreement to try to safeguard access of critical materials to the West. It includes things like price supports and targeted investment. Price supports are very, very important because, of course, the Chinese having a dominant position could undercut the price of a new rare earth source and basically control again the marketplace. And so price supports help buoy the return on investment to rare earth investors, which is going to be very important. The Trump administration has created a $12 billion rare earth stockpile to counter China. So like we have a strategic oil reserve, we have a strategic critical minerals reserve, and we want to build on that strategic mineral reserve and open it up to public partners. And we've identified 3 commodities firms that are going to be sourcing rare earth materials for our strategic stockpile. We're using diplomacy to try to build a counter to the Chinese supply chain. So forming a trading bloc with a bunch of countries, 11 countries so far have signed up to work cooperatively to develop rare earths that are going to be sourced separately from China. And technology is going to be very, very important. You know, I mentioned the control that China has on rare earths globally, but China has demonstrated its ability to hinder economic growth, particularly in Japan. And so Japan is working very, very hard to try to become less dependent on Chinese rare earths. And just a month and a half ago, the Japanese made an announcement they had discovered a huge reserve of rare earths in the seabed off of an island off the coast of Japan, okay, which they control. And according to their estimates, it contains about 16 million metric tons of rare earths. Now, there are 16,000 feet down. So again, it's a technology problem, right? But it goes back to these are desperate times, right? And countries are looking for sources outside of China to provide them the opportunity, even if they don't mind this. It is a trump card in their back pocket that can help alleviate, or at least be used in negotiations with China to keep open the rare earth supply. But I think we can't. My personal opinion, I will raise my hand when I have an opinion. A personal opinion, I'll raise my hand. I raise my hand that there's no question in my mind that diplomacy can only be part of the equation. We have to, diplomacy with China can only be part of the equation. We need to expand diplomacy with other countries and our partners so that we are not 90% dependent on Chinese rare earths. I guess that's not That's not a controversial position, I don't think. But what can we do, and what are we doing domestically besides our outreach to our partners to manage the strategic vulnerability? And really, there are three things that we're doing. We're looking to rebuild our domestic capability. We're looking to reduce and replace rare earths where we can, and use technology to reduce our reliance on rare earth materials. And we've just started a recycling effort, small at this point, but there's an opportunity to recycle rare earth materials. And we're going to just step you through some of these. So I mentioned the Mountain Pass, California rare earth mine, but it turns out that recently we've been finding rare earths in quite a few places around the country, either rare earth mines or rare earth processing. So we are on the road to developing either mine or processing capability for rare earths domestically. And let's talk a little bit about those. So if you've watched the 60 Minutes segment last Sunday, they talked about this company called MP Materials. It has changed hands several times. It's now in the hands of some hedge fund investors who are very bullish on bringing the MP Materials mine back online. And actually, timing has a lot to do with how successful you can be. All right, they saw the opportunity here and the pressures of a single source of rare earth materials. They put two and two together. They made a very good and cogent pitch to the U.S. government to be partners with them to help develop a domestic supply chain for rare earths, since we do have quite a lot of rare earth materials already in place and already ready to be recovered. So it was a public-private partnership, which involves loans from the Department of Energy, preferred stock. So the government is taking an equity position in this company. And the company in return has decided that they are going to build domestic magnet production capacity at a facility called their 10X facility. And by 2028, that should be online and producing magnets domestically here in the United States. So we're not only dealing with the actual mining and recovery, but purification and producing end products domestically. And as part of this agreement, the Department of Energy has decided that they are going to provide a floor price for rare earth magnets, about $110 a kilogram, which will prevent the Chinese from undercutting us and allowing a return on investment for the investments that they put into MP Materials. Another company called Energy Fuels that specializes in processing radioactive materials has got into the rare earth business. They are producing, or they are in the process of building a plant to process heavy rare earths. These are the materials that are on the bottom part of that periodic table in Utah. And they have built a commercial plant for neodymium and praseodymium oxide in Utah itself. They are already producing 99.9% material of some rare earths that have been sourced from Florida and Georgia, even though this is a small scale facility. And recently, they had an announcement just a couple of weeks ago that they have produced terbium at this facility, and they're looking to scale up. So we have other sources of rare earth processing being developed in the country, and they have several rare earth partners that have agreed to take these materials and make magnets from them. Wyoming is a very interesting story. There's a company called Ramaco that bought a coal mine in Wyoming. It's Ramaco is located in, I believe, West Virginia. Okay? They own coal mines in West Virginia. They bought a coal mine in Wyoming. And some bright engineer at Ramaco said, hey, you know what? We got the report of the rare earths when we bought this facility, but let's do another measurement. And they did, and they found that, in fact, it has a tremendous amount of rare earth materials in that coal mine. So a $2 billion investment in a coal mine, they purchased a facility that has an estimate of $37 billion of rare earth materials in it. Now, they have to take it out of the ground, they have to process it, they have to purify it. But this is, as I said, sometimes timing is everything. And they bought this facility. Now they're looking at how they can recover the rare earth materials because they're even more valuable than the coal that they were planning to recover. And the state of Wyoming is supporting them in building out the rare earth capability in Wyoming. There was another rare earth find in southern Wyoming, which again is a positive thing for us in terms of sourcing materials. But it all gets back to what is the concentration of the rare earths, and is it high enough that we can economically recover them? In Nebraska, there was a source of niobium and scandium. Niobium and scandium are on the bottom row of the periodic table, and scandium is very, very important because small quantities of scandium significantly improve the mechanical properties of aluminum, which is vital for aircraft. And so if we've got a source of scandium, that would be very, very important for us to build and develop. And so this company, Neocorp, is doing that. The Department of Defense has awarded $10 million to Neocorp to subsidize the development of the scandium source in Nebraska. And another company, USA Rare Earths, which also deals with radioactive materials, has partnered with the US government. The government has put an equity stake in USA Rare Earths to extract rare earth materials from Texas, to process it in Colorado, and to make magnets in Stillwater, Oklahoma. And a company called RE Alloys. Now, if any of you are following the stock prices of any of these things, you'll notice that they go up and down every time there's a new press release, and they're all trying to outdo each other. But a recent press release from this company called RE Alloys came out where they are actually looking to employ a new technology developed in Saskatchewan by the Saskatchewan Research Council, SRC, that can significantly reduce the environmental impact of processing rare earth materials. And so they are looking at trying to bring that technology into the United States and provide a way of processing rare earths that is more environmentally benign than conventional ones. Recycling is another option, and Apple announced that they're going to be working with MP Materials to supply them with old cell phones and computer chips and iPads that MP Materials will then recycle the rare earth materials from them and put them back into the supply chain. This is the largest investment in rare earth element recycling that I'm aware of, and Apple has committed $500 million to this effort. And the universities are looking at other ways of improving the capability of recovering rare earth materials. Penn State announced that they had a plant-based material that can recover rare earth materials. It's basically a filtration device that when you have dissolved rare earths, you can recover those rare earths using filtration. And University of Texas also developed a way of doing e-waste recycle and putting that back into the supply chain. So there's a lot of activity in rare earths, a lot of investment going on, and we'll see if any of these technologies actually become commercial. It's one of the challenges, and I dealt with this a lot in my previous job, taking an important scientific find and making it into a commercial reality. Let's see if that happens. And of course, we are always looking for ways to reduce our reliance on rare earths. So Texas A&M has put out a press release saying that they have a way of making electric motors using fewer rare earth materials. And they're not alone. A German company, ZF Friedrichshafen, is one of the world's largest auto suppliers, and they have been working on electric motors without rare earth materials and have built demonstration motors that may one day become incorporated into the next electric vehicle. And so automakers are all looking at trying to reduce and eliminate rare earth usage because the cost of those parts is going to go up as we reach the floor price of the U.S. Domestic rare earth magnet supply. And so, I was talking to, is it Charlie? I was talking to Charlie earlier. He said something very, very clear and crisp. He said it's a balance between the commercial interests, the military interests, and the diplomatic interests. And how do you balance all those three? And it's a moving target, right? But you need to move forward on all fronts and see which ones. It's like Darwinian evolution. You have to make mutations and then see which ones survive. And I think that's what we're working on. And major suppliers have committed to reducing or eliminating their usage of rare earth materials. So in summary, rare earth materials are absolutely vital for everything that we do. In the morning when I get up and when I go to bed, I'm touching something that has a rare earth material in it. China is the leading miner, processor, and exporter of rare earth materials, which has led to a strategic vulnerability for not just the United States, but the entire Western Hemisphere. And we're all looking at ways to try to reduce our reduce our reliance on rare earth materials, particularly in light of the fact that we expect that the need for rare earths is going to only increase over the next decade. So we go back to diplomacy and working with our partners to try to rebuild and expand our supply chain for rare earths. We look at recycling capabilities, and this is, is becoming important here in the United States, but it's also becoming important in Asia to recycle materials that contain rare earths and replace rare earth materials where possible. And with that, I will conclude. Thank you.
It was very stimulating, and informative talk. We will forego the coffee break and go into the Q&A portion of the program. But feel free to get up for coffee or use the restroom. But Mike will pass around a mic for each questioner. So just raise your hand and Mike will bring you the microphone for your question.
1 second, we'll get the mic over to you. Just so the folks on Zoom can, this gentleman had a question, that young lady had a question. This gentleman was, yeah, he was first. Yeah.
Thank you very much. So my question is, I've heard some talk about mining asteroids, and as far as space goes, is there any more, or is there a better source for rare earths in space than here on Earth?
I've heard that too. Again, I'll raise my hand in opinion. My opinion is that we've got a lot of rare earths here on Earth. We just need to find the best way to get them into our hands and into our country. I think it'd be very expensive to do recovery, space-based recovery.
Yes, I have two questions on things you showed. First, on Greenland. On Greenland, you showed us where the rare earths.
Yes.
Where? How does that relate to where the people are living in Greenland? Is it closer?
Most of the people in Greenland live in the southern part of Greenland. But they're relatively small communities that are actually on the coast. There are not too many people living internal to Greenland. And most of the ways they get to each city is by boat because they're coastal communities. That's why there's few roads in Greenland. Some of the two dots on that chart that were on the lower end of Greenland are closer to
lower left.
Yeah, lower left. Those are the two that have the highest concentrations of rare earth materials on Greenland. And there are some communities around that area. So there may be some impacts there. And I know that I was watching a documentary on this, and there are several, there's a lot of agriculture along the coast of Greenland, a lot of sheep farming and that type of thing. And so they're very much concerned about the environmental impact of those
Yeah, that's the trouble. And the other question is related. You showed in California the mine was bought by MP Materials.
Yes.
It's hard for me to believe that with California's environmental laws that they would allow any mining to go forward. What do you think?
Well, I think this is a good question. The question is, you have to monitor, right? If you have an environmental concern, you have to monitor for the environmental concern. I think there are a couple of issues that I don't have a direct answer for you. Okay, the fact of the matter is the mine is in operation. Okay, it could be that the mine does not have as much radioactive material as other mines do. I don't know the answer to that. It could be that it's very remote. It's on the border of Nevada, off the 15 actually, on the border of Nevada. It's pretty remote. I'm sure that there are environmental restrictions in California. I know that the price of rare earth materials in the 90s was going down, and it just didn't pay to introduce the environmental remediation that was required from the state to continue production. But obviously something has changed, and there's a national imperative. We need to find a way of balancing the environmental impacts with the greater national interest, and states have an important part to play with that. Right?
I have two questions. Geologically, is there a reason that you always find radioactive materials with the rare earths? Is there a reason for that? The other question is, money makes the world go round. Wouldn't Denmark like get a cut of the action that we're extracting this very expensive material? And so that should make them happy, besides sending us drugs that help us stay skinny.
Yeah. So rare earths often come from radioactive decay of other materials. So that's why they're often associated with radioactive compounds. The citizens of Denmark may see a big dollar sign with Greenland, but the citizens of Greenland have an important say in it. And they are very concerned about environmental impacts that they won't have control over, right? And this is one of the challenges in any of these situations, the challenges of balancing the national interest of the country or the interests of the Western Hemisphere and the interests of the local population. And how do you balance that? And there are way smarter people than me that spend all their time trying to figure out what the best balance between the two is. Greenland has its own independent governance structure, right? And so they pass their own laws, and you'll have to convince them that it's okay to mine something that has radioactive material and what kind of environmental controls are going to be required. So money talks to an extent, but if you're talking about what the impact is to other industries on Greenland, agriculture, for example, the native populations in Greenland, that has to be balanced.
Next question right here. Armando?
Oh, hi. Are there any reasonable prospects of finding some man-made substitutes in the future for this?
Man-made substitutes are really difficult. It's difficult to make an element from other elements. It's not impossible, but it's difficult, right? So many of these things, all the elements that are used in all of our bodies was made in space. Okay. Now we can make them. We have the technology, but it's very, very expensive. And you need to be able to make tons and tons and tons of this, right, to meet the demand. We just don't have the technology for
that. Next question right here.
Yes, we've spoken about rare earths kind of as a group. Are there any particular elemental vulnerabilities that we have, particular elements we're missing?
Well, vulnerability in terms of sourcing, scandium is a very important one, because I think we import 100% of all the scandium that we need. And if we're going to build fighter planes and Tomahawk cruise missiles or whatever else we think we're going to need for the future, we're going to have to find a way to get access to scandium, either through an ally or developing it domestically.
Dr. Thomas, I saw something a couple months ago just about the political situation south of the equator in Africa and the areas. Is the materials coming from there? Do they go back to China for processing, or do they go the full thing down there that they could be taken over or made commercially feasible for us to acquire?
Yeah, so I think you're talking about the Democratic Republic of Congo and some other countries. They do have rare earth access to rare earth minerals, right? Mines. I'm not sure they have processing capability there. I'm not sure. It's likely that they probably send it to China. It's likely.
Thank you very much. Great presentation. In your opinion, of those responses, which is the most fertile area for development? Is we more likely? It seems like recycling would be a good way to go, but what are the other probabilities?
So again, my opinion, I'll raise my hand. Okay. In my opinion, we're doing the right things in first finding sources that are mineable. Okay. We pointed out a couple of those. We're doing the right thing in trying to develop the technical capability of processing them domestically, right? We're doing the right thing in trying to partner with other countries. But there's not a one solution to this. I think recycling, we're not going to be able to recycle our way out of this problem. It's going to be an important component to solving the problem, but we will not be able to recycle 100% of the materials that we use back into the supply chain, not economically, right? And so it'll be a part, but it won't be the solution. I think these partnerships that we're doing with Australia and other countries to find sources of rare earth materials that can be processed is one step. Putting the price floor is another step, because one of the worst things you can have is to be undercut by your competitor, right? There's a downside to that, and that means all of our cars and all of the wind turbines and all this, the solar panels are going to be more expensive. But is it worth the price for reduced vulnerability? And this is the question that every country is dealing with, right? How much are they willing to pay to reduce their vulnerability from China?
Thank you very much.
Okay.
Excellent presentation. Excellent. As a reminder, next month, April 24th, we will have Admiral Charles Marcholio be our speaker. And we look forward to having you all again. Thank you for coming.